This is week 13, day 3. Today we're going to include this particular lesson. Our topic's actually from exam 5 rather than from exam 4. You will need to watch this in order to be prepared for Alex's homework. Today, what we're going to do is we're going to study systems of equations. Very similar to what you see in the movie Top Gun. You know, we had Maverick and we had Jester in the original Top Gun, and they were trying to shoot each other down. Well, in this case, what we're doing is we have two equations that produce lines. These two lines can have an included point of intersection. Okay? That particular point of intersection would be called the solution of these two lines, which we also call a system of equations. Now, so this is very similar to that. There are 3 ways to calculate the solution to a system of equations, and also there are 3 types of systems of equations we'll get to a little bit later. The 3 methods of solving systems of equations are by graphing, which has limitations due to the graph paper itself, by the addition or elimination method, and by the substitution method. Now, it's my intention to cover the elimination method before the substitution, which is a slight departure from what it says on the pacing guide. I believe it's a little easier to do substitution after you've done elimination first. Okay, here are a couple of equations. Now, the first thing what we're going to do is we're going to look at a pair of equations. We're going to take a point, and with that point, we're going to see, is it a solution to this pair or system of equations? So what we do in this case is we take the first equation, we substitute the x and the y value into it, and we get an answer. Then we take the same point and substitute it into the second equation. Okay. So in that particular case, it shows that we get the same value. Now, if we look at this, in the first equation, it checks that it's true that it works for it. Now, the second equation, however, if we put this -3 in here and the 5 in for the y, we get a value of 3. Well, we test that then and see if that indeed is true. Is this equal to 3? Well, no. So therefore, this point is not a solution to this system of equations because it has to work for both of them. Here's another, a little bit more complicated point. In this case, we're first going to substitute into the first equation the 0, the 1/2. We simplify that a little bit. This wipes out. Half of 10 is 5. 5 equals 5. This point checks for that equation. For the second equation, we put in the 0. That wipes out. We put in the 1/2. And half of 6 is 3 and negative in front of that. So yes, it does check. So that means that this is actually the point of intersection where these two lines would cross. Now, here's just kind of a definition that we've really gone over already. A system of equations is two or more equations considered at the same time. Okay, this is repetitive. The solution to this is any ordered pairs. Here's an example that are a common solution to these that will check with both of those. I said there were three types of ways of finding a solution. One of them is graphically. Okay, here we have that. We graph the first equation, we graph the second equation. We see their point of intersection, and then we write down that. So in this particular case, there we go. Now, what they're telling us in this case, that the 0.25 is a solution of those two. If we take this one and we graph it, and we take this one and we graph it, we come up with the common point. Now, something that's not shown in my slide that for the most part you're going to need to do in order to easily graph this, let's put this in y equal mx plus b format. So we would have negative y equals negative 5x plus 5. Then we would divide both sides by -1 every term and get y equals positive 5x plus or minus 5. Okay? So that would be this equation. So if we were to graph that, that would just make that easier for us to graph. I left out the plus sign. Then we would have a y-intercept down here at 5. Okay? And this particular graph would have a slope of 5/1. Okay, so we would go up 5 and over 1. And that would be this red line. This one would come down here like this. And up 5/1, and we would graph the line. Likewise, we would do the same thing for the other equation. We would take this over to the other side, giving us negative y equals negative 4x plus 3. Okay, divide everything by -1. And we get y equals 4x minus 3. So in this case, actually I drew this incorrectly. This one goes down to 5, this one goes down to 3 for the y-intercept. And you graph this one with a slope m of 4/1. So you would go up 4/1, up 4/1, and then you would find their common point of intersection here at the 0.25. So that's the general process for graphing. Now, what could go wrong? Well, perhaps this point of intersection would be out of space somewhere here. If that's the case, we can't read accurately what the value would be. So your answer at best would be an approximation, and if you tried to check it, would probably be very difficult to check. So that's the disadvantage of the graphing method. Now, I said earlier, there are three types of systems of equations, okay? And we're getting to begin into this. We're not quite there yet, but there are two classifications, and you are expected to know these classifications. If they have at least one point in common, then they're called consistent. Here, a common solution, they are consistent. Okay? If they don't, then we call it inconsistent. Likewise, we have dependent and independent as a classification. For dependent and independent, basically, if the two lines exist independently of each other, they're independent. The case where they would be dependent is where it's actually the same line or overlaying lines, just in a different form. And we'll go over some examples of that. Now, if there is one unique solution, one point, okay, then the intersecting lines have one solution is called consistent. It's possible you could have no solution, no point that they share in common. Now, that would be the case where you have parallel lines. Okay, because they do not share a point, we call them inconsistent. And then there's the third possibility. You could have infinitely many solutions because basically it is the same line with just different multiples of the numbers in the equation. Now, we call those dependent. If they are the same line, we call them dependent. They are consistent because not only do they share one point, but they share all points. Now, here's a graphical description of what I just said. Here we have totally independent lines that intersect somewhere in space. These two lines have different slopes, very different slopes. Okay? They result in one solution, one common point. They are consistent because they share at least one point. They're independent because they exist independently. Parallel lines. Parallel lines share no common points. And we'll talk about differences in the slopes for parallel and perpendicular lines a little later. And these two exist independently. They will have each their, now, these two will have the same slope. As one of their characteristics. And then we have what is really the same line. Now, they're identical, they're just in different forms. Perhaps one is a multiple of the other. Okay? They are consistent because they share all points. They are dependent because they depend on each other. They're all the same points, the same lines. We also have perpendicular lines, but perpendicular is a specialized version of this one. Okay, here's our first equation in this problem. There's our second equation. Now, when you do the addition by graphing in this case, it's best to put them in y equal mx plus b form, which is what I have done right here. This is y equals mx plus b. This one is already in y equal mx plus b. Now, based on those two variations of this, we graphed the two equations. Okay, here was the first one, here was the second one, here. And they share a common point of intersection of the point 2, -1. All right? So, let's classify these. They're totally independent lines. So they're independent, they share a point, they are consistent. And here's just a check of those values to see that that point of intersection actually mathematically correct. Now, the elimination method, as I said, we're going to do it first because I believe it's a little easier for you to get into the substitution if you do the elimination first. What we're going to do is we're going to find what I call opposite pairs. Opposite pairs of values for the same variable, okay? So let's go into this. I've got these two equations. Now, I said I want an opposite pair. What I'm calling an opposite pair is like this positive 30x and this negative 30x. Okay? So, how did I attain that? Well, in this case, I had to take the first equation and multiply everything in that equation by 5. 5 times 6x is 30x, 5 times 2y is 10y, 5 times 4 is 20. The second equation, I had to multiply everything by negative 3. In this case, negative 30, negative 21, positive 24. Now, why would I use these two first? Because basically, this is a common denominator problem. What is the least common multiple of 6 and 10? Well, it's 30. And how do I get both of these to 30? Take that one by 5, take that one by negative 3. So that's the process we're using. So here is my common pair, and those will always cancel each other out. What that leaves me is I can combine these two y's and get negative 11y. I can combine the numbers, get 44. Doesn't show it, but divide by negative 11, divide by negative 11, and I get an answer of y equals negative 4. That is this value of the point of intersection. Now let's find the x since we have the y. In this particular problem, we take either of the two equations, probably the simplest one, and I substitute the y value and solve for x. So here, then this gives me my x value. And that's the process of by elimination. That gives us this common share point. Because it has a common share point, then classification-wise, that means that it is 1, independent, 2, it is consistent because it shares a point. Now, I'm going to work this problem another way. This time, instead of eliminating the x's, I'm going to eliminate y's. Just so I can show you it doesn't make any difference. So if I have the common denominator, least multiple of 2 and 7 is 14. So to get 14 here, I need to multiply everything by 7. To get 14 here, or negative 14 here, an opposite, then I need to multiply everything here by negative 2. So 7 times this one would give me then 42x plus 14y equals 28. If I take negative 2 times all of these, I get negative 10x, negative 20x, minus 14y equals positive 16. Now I add those two. First, these two are my opposite pair and cancel out. Here, I end up with a positive 22x. Over here, I got the same sign, so I add. I get 44, divide both sides by 22, and x equals, in this case, 2. What about the y value? Well, it's a similar process to this, except now I'm substituting the x value. So I've got 6 times 2 plus 2y equals 4. 12 plus 2y equals 4. Subtract 12 on both sides, and we get 2y equals -8. Divide by 2, y equals -4. So you see it'll work either way. It doesn't matter which side the x's or the y's that you decide to eliminate. It's just a slightly different process. Now, for this addition, which is also called the elimination, this is suggesting that you have to put it in standard form, okay? I'm saying you don't have to put it in standard form, but what you do have to do is you have to have the x's, the y's, and the numbers in the same relative location. You could have slope intercept y equal mx plus b form in both equations, and that would be okay. It's just a little easier if you have it in standard ax plus by equals c type form, okay? Now, let's go on from this. Here are 2 more equations. We look for an opposite pair. Right now, I don't have one. I could use 10 as my least common multiple here, or I could use 3 as it here. In this case, it's easiest to deal with the y's, because all I've got to do is multiply this one by 3 and that one not by anything. So I'm going to multiply that by 3. And so I'm bringing across the first equation. Here's my modified second equation. Okay. And I have an opposite pair right here that will cancel out, leaving me 17x -68. Well, very conveniently, 17 goes into 68 exactly -4 times. So that is our x value of our ordered pair. Now we go to find our y value. We take either one of the equations, whichever one of them looks more simple. Well, I would choose this one because it already has 1 y. So I replace the x with -4. Take this -20 over to the other side by subtraction or addition on both sides. And then divide both sides by -1, getting an answer of 6. Have ultimately the answer -4, 6. Since I achieved a unique point in this case, that tells me that these 2 lines are both independent and consistent. Now we've got symbols which get just a little more difficult. I still need an opposite pair. I can use 10 here, or I can use, in this case, 0.3 for my opposite pair. So what I'm going to do is I'm going to multiply this by 10 to get rid of that decimal point. And then I'm going to multiply this one by 100 to get rid of those two decimal points, which modifies these equations to this. Now, you would not have to do this. You can work this as decimals, but it's always less error prone if you get rid of the decimals first. Now, I still need to either use, in this case, 100, or in this case, 30 for my opposite pair. Well, I'm going to multiply that by 2, that by -5, showing that I'm going to have my common denominator of 100 for this. So here are my two modified equations from over there. These two will cancel. This will give me 56y, and that'll give me a -112. Well, 56 goes into 112 twice, and the negative. So now we take -2 and put it into either one of the equations. We can do it in this format, but it's easier in this format. So I substitute the -2 here, and I get 50x. I take this -6 over to the other side by adding 6 to both sides, getting 20. And then I get x equals 2/5 or 4/10. So my answer would either be that, or it could be 2/5 -2. Either answer would be acceptable. Here we have fractions that we need to deal with. The easiest thing would be to clear the denominators first, but again, you don't have to. Here they're going to multiply 3 times every term to get rid of these 3's in the denominator. Here they're going to multiply 2 by every term to get rid of these 2's in the denominator. So I've now done that. As it turns out, I've almost got an opposite pair there, but I've almost got an opposite pair here too. Well, I got to get it on one of them, so I better take one of them by -1. So I'll do that, resulting in this equation that I just brought down. And this is my modified equation. But look what happens on this problem. These go to 0. These two also go to 0. And this is -3. I've got an unreal situation. Okay? What that means is that these two equations do not have a common point. Okay? Well, what kind of lines don't have a common point? Parallel lines, whether they're this way or whatever angle in space they might tend to be. So you get an answer like this, an unreal answer. That's a clear notification to you. One, they're consistent because they don't share a common point. Are independent with this inconsistent no solution thing, then they happen to be parallel lines. Now, on a test question, what kind of answer would I want to see if you got this result? I would see that they're inconsistent. I would see that they are independent, and that's not written on my slide. And I also want to see the word parallel lines showing me that you recognize that these are in fact parallel. Okay, now here's another example. Solve this system. Okay, I multiply equation 1 by -2. Uh-oh, look what I got. Here I took this equation 1 by -2. Those two cancel, these two cancel, I got another set of parallel lines in this case. Now, what I've got over here, this is like the last problem. This one is different. This is the third type of possibility I told you we could have, okay? That we could have no points, all points, or 1 point. So, in this case, here are my two original equations. We're just labeling them equation 1 and 2. You could call them A and B just as easily. So I'm going to multiply equation 2 by -3, so I've got an opposite pair. Well, in this case, once again, all my x's and y's cancel, but in this case, so do the numbers. This means that I got a universal truth. Okay? That means that these two lines are actually the same line. Okay? If you notice, if I 3 times 3, I would get 9. If I took 2 times 3, I would get 6. And if I took 16 times 3, I would get 48. So in other words, this second equation is just the same as the first one, except everything is divided by 3 to go from this to this, or multiplied by 3 to go from this to this. Okay, and that would be a common characteristic on these lines that are the same line, which are dependent, but yet they are consistent because they share all points, infinitely many solutions. Every point on one line is a point on the other. Okay, here's another one. Now we're getting a little more complicated. We've got to do a distribution before we can do the addition or elimination. So in this case, we distribute this 3 and ultimately get that. We distribute the 6 and ultimately get that. We look to see, do I have an opposite pair already? No. So I've got to adjust one or the other of these. It's easiest to multiply this by -6 to get an opposite pair instead of multiplying this by 4 and that one by 3. So we're going to multiply this by -6, resulting in this equation. We just bring over the second equation, and in this case, these two will cancel. Leaving this, which is 22 - 22x equals 44. Divide both sides by -2, and we get that. So now we put the -2 into one of these simplified equations. Doesn't matter which one. So here's our x value of -2. We continue with that process, and we y equals -1, leading to an ordered pair of -2. 1, -1. That means we have a single point of intersection. They are consistent. They are also independent. Okay, another example. That one we're going to multiply by 3. This got a opposite pair. Subtract, and actually these are the same numbers we had on our previous problem. Okay. Looks like I've got a duplication of the same side, 2 of the same sides. Okay, now we're going to move to the substitution method. In the substitution method, we isolate one variable in one of the 2 equations. Then we use it as a substitution value into the other equation. In either case, then the second step for the second variable is just like we're doing for addition already. All right, in this case, this one will be the easiest one to get an isolated variable on. So in this case, we take the 5x over to the other side, divide both sides by a negative, resulting in, the y to be on the left if you prefer. So we get that. Now, what that means is this right here, this part right here is going to be my substitution value that I'm going to put right there. So I have taken this y value, this is equivalent to y, and put it into the other equation. And it has to be in the other equation. Now, here we go. I start simplifying this, I distribute. And at that point, I combine terms, and I end up with 17x equals negative 68. I divide it, and I get x equals negative 4. Now, the second part of this is just like we've done before, except I use this isolated value because that's the easiest way. So here we have that isolated equation. We do the substitution of x equals negative 4, and we get y equals 6, producing a point of intersection of negative 4, 6. Here are the graphs, respectively, of the two equations that we originally had. Let's go to another one. Once again, this equation, because it's got a 1 in front of it, is going to be the easiest one to isolate. So here is my isolation, and this will be my substitution value. So I take that value into this equation, into the other equation, and then I start simplifying. So I get x equals 1/3 for my first value. Then what I'm going to do is take that 1/3 and put it into my isolation equation again. There. And it simplifies to 4. So here is my point of intersection in this particular problem. We're going to check it. It checks in both cases. And in this one, because it's got fractions, we're not going to worry about graphing it. It'd be hard to get an accurate graph. Okay. Another pair. This time we got a fraction. This time we already have an isolated value. So this will become my substitution value. And where are we going to put it? We're going to put it right here. So there's my substitution value again. We're going to substitute it here. Then we're going to simplify. I'll take this bottom 7 into my next slide. We're going to distribute that negative 3 and continue simplifying, and we get y value equals 3 for our first value. So now let's solve for the x. Well, the easiest way is to go back to that substitution, that isolation equation. So here we have this, we're going to replace this y with positive 3. Doing so, then we end up with x equals 1. Here our point, single point of intersection is the point negative, 1, negative 3. And it checks in both cases. Once again, we already have an isolated value, so this will our substitution value. Where are we going to put it? We're going to put it right in the other equation. Do the substitution. We simplify. And we got another one. Before we got a 0 equals 0. Now we have a 30 equals 30. What is the implication of that? That means that any real number will produce a correct answer. So therefore, these are the same equation. What are these? These are overlaying equations. Okay? All solutions work. Any point in one line is also a point in the other line. These are consistent. They're going to share all points, but they are dependent because they're the same line. I want to see the word same lines on your answer as well as dependent and consistent. Here is the set notation answer for that thing. Basically, you're saying X is any real number. Here is another set. I've already got an isolated equation, so this one's kind of easy. We're going to replace the Y with this. We simplify. And in this case, we get X equals 1/2. We go through, substitute it in, and we get a unique point. We got a unique point. These are dependent distance lines. Now, here, notice my variables are not, and numbers are not in the same order. If I'm going to do it by the addition method, I've got to arrange them in the same order. If I'm doing it by the substitution method, then I've already got an isolated variable. In this case, we're doing it by addition. And we get that, once again, we get an equality statement. That means that these are the same lines, okay? They are both consistent and dependent, and they are the same line. Okay, look at this one. We're clearing the denominator. Common denominator of 5 and 2 is 10. So I multiply each term by 10. All three of them. Now, I'm going to solve this one by the addition method. So, I have converted this into this equation. So now I have these two. I've got to find an opposite pair. So I'm going to multiply the top one by 2. Just bring the bottom one over. There's my opposite pair, and I've got a pair of opposite pairs in this case. And these conveniently also give me 0. So since I've got an equality, once again, these the same line, all points are shared, they are consistent and dependent. What about word problems? At this point, this is where we're going to take up our next particular class period. So we're going to stop this one at this point.